comments, and that was when I'm doing amplitude analysis in FEA for a transducer, what's the role of bolt pretension and clamping in that analysis? Do I need to put clamping in the device, in the transducer where the flanges are, or do I need to leave that open, or what to do there? And also, what do you do with bolt pretension? So I'll answer the pretension part first. And what I have to say about pretension is when you apply the bolt pretension and you get your transducer kind of, the crystal squeezed down, the bolt kind of stretches. When all that happens, technically the mode, the frequencies change, and you might have a different analysis altogether, and that would be true if your structure actually deforms significantly. However, due to the stiffnesses involved, you are going to not really displace a whole lot, and the shape of the transducer is not really going to change. Yes, if you do some exaggerated fine element like deformed model, you may find like this center bolt gets like really thin or something, but in reality, it is hardly a change in the structure. And the actual changes that I've seen actually that occur, in modal analysis or in amplitude analysis for harmonics are actually more due to the contacts, the different types of contacts you have to introduce in order to perform that model. So it actually ends up being incorrect. I've seen the results being incorrect, and you can verify this because you can put a pretension of like a very small pretension and see how the model is different from a model that doesn't even include any pretension physics at all. So that would be one thing. So the deformation is really small, although it's significant. You need that, and the strain is ultrasonic motion is really small, but basically the shape and geometry doesn't change much. So I would not put it in, but you can verify how much effect it makes. But you be sure to compare it not to a model with like very small pretension loaded, but also to a model that doesn't even include that step at all. So you can really be sure that the new types of contacts that you have to introduce in the physics that you have to introduce don't negatively or don't add an additional flavor to your simulation that you did not want, because the standard is using no pretension. That's what's been classically done, and it's worked very well. So I would first mention that. Secondly, for clamping, this is kind of interesting question, whether we should actually put like fixed boundary conditions. So first of all, in real life, fixed boundary conditions never exist. Actually, in very rare situations, not very rare, but a lot of times you're not screwing down to the clamp. Like in a surgical transducer, a lot of times the edges aren't screwed down. They're more like suspended in an O-ring. So it's a bit of a softer contact. So basically by putting a fixed boundary condition, you make it extremely rigid. And that does change modes if you do have that fixed condition off center. The other thing that fixed boundary conditions don't do is they don't disrupt the quality factor. That's what clamping does a lot. Like if you clamp in the wrong place, not only will you affect the frequencies that are operated, but you'll also end up damping the transducer, which is not shown, which doesn't happen with the fixed boundary conditions. So this is what I would kind of recommend. So I would recommend not clamping, but just know that, you kind of realize if your transducer is actually, are you clamping at the nodal point anyway? Because if you are, then it'll provide little change anyway. So if you actually are clamping at the point in your real device, then you don't have to worry about it. You can still optimize your transducer regardless of your actual clamping. But the issue with fixed boundary conditions and adding that in there is that it provides a stiffness that's not real for most cases, and also provides no damping. Your transducer can resonate with the same quality factor. There's no damping introduced, so it kind of doesn't give the whole story. So therefore, I simply note that in my mind, and I still would continue to optimize your transducer in a free condition, but just with a note that I am clamping. Oftentimes that clamping part is an experimental optimization. It's not precisely something you completely do in FEA besides perhaps just locating the nodes. And that's what I have to say there. So keep your simulations simple, use them to advance your design, but just to know that your iteration to your practical transducer is absolutely necessary. You can only go so far in FEA. I've seen efforts to include so many things like, what are the friction contacts between crystals, or, even if you want to include electrodes or not, and you're really trying to get the bulk behavior out of it. And a lot of the optimization and the troubleshooting does happen through experiments, which afterwards you might look to consider optimizing that transducer based on what you've seen, but you have to, including too many physics in your FEA is a recipe for getting stuck in your analysis. And analysis is never a product. What you sell is the actual, and what you experience is your actual device. So I'll leave you with that. So today, in episode number 58, we covered finite element analysis and whether and how we should include pretensioning. I think for a static stress analysis to see how the stress distribution is over the crystals, I think it's a great idea. You need to do that in order to ensure your crystals are compressed with the level of oscillation that you expect to see. And also for clamping, it may be useful to do a clamping type of analysis just to see how frequencies change if you are indeed not clamping at the nodal position, or you have a very rigid contact. You do want to see if those flanges have their own resonances, which can lead to other types of flange kind of design where you put like undercuts and you make it like a different shape in order to, and different length or diameters in order to optimize and reduce unwanted modes. But I would consider that analysis separate rather than the general optimization of the transducer for analysis like in the horn and that. So I hope you enjoyed this video, and I will catch you in episode number 59, which we will continue to work on our dental scalar and probably displacement measurement. Thanks for watching.